Hey guys, so in this video we'll be learning how to find the area of a circle. Yes, you heard me right. The simple shape, the simplest shape known to humanity, but which holds an irrational secret, right? So, yeah, that's exactly what we'll be doing in this video. So, the title is of course gonna be an overwhelmingly complicated method to find the area of a circle. So you might be wondering, like if you don't already know how to find out the area of a circle, like the proof behind it, and go through the rigorous integration, then this wouldn't make a lot of sense for you, because in school you would have just been taught to know that the area of a circle is pi r square, but you can actually easily derive it through integrations. But in this video we'll be looking at a very complicated method. When I say very, it's not actually that complicated, but it's very unnecessary, and the entire focus of this video is not for you to learn or to follow this method, but instead to give you insight to like the various methods possible. So this is how it goes. Like ideally you would be setting up integrations like this, right? You would take up like an elementary disk, I mean a ring, at a distance r, like small r away from the center of the circle, and the circle itself has like a radius of capital R, and this tiny ring has like some amount of thickness, which I'm shading over here, and you basically add up infinitely many of these infinitely thin rings, and that's how you'd be getting the formula for s pi r square. But we'll be looking at a different approach, and in fact I'll even solve this and show you really quick how simple it is with this method. So easy method first. So we can write dA is equal to the area of this very thin strip, or ring I must say. Like let's say that you have the ring and you take a scissor and like cut it like that, and you happen to like lay it down flat. This is essentially what you're gonna be getting, right? The length of it is gonna be 2 pi r, which is the circumference, and let's say that it has a thickness of dr. So this tiny ring's area is basically 2 pi r dr, and summing up all of these tiny areas gives you integration 2 pi r dr, and the radius of course spans from 0 to r, so you'll be getting 2 pi r square by 2, which just simplifies to pi r square. You might be like, this is so simple, why would I need another method? But that's where calculus and the beauty of math even lies in. By solving it in complicated ways, you get insight to like different methods of solving the same problem, and that refines your mathematical skills. So you might be wondering, where exactly does this complexity even hide? Because this seems like no complicated task, but this is where things get spicy. Instead of measuring rings from like the center, what if I was standing on the circumference itself, and I was measuring these kind of circles. If you think about it, you might be wondering, okay, it's possible, but how am I gonna set up the integration? How am I gonna get the equations and like get them to relate to one another? Well, that's where I step in, and that's where you as audience get to learn something new, right? So, like the various elementary strips are gonna look something like this, and you're gonna have something like this, and like all across. So now let's define some variables. So let's say that this is of course your capital R, and let's connect like the end of the like wherever the circle intersects the, I mean wherever the arc intersects the circumference, let's just connect those lines, right? And let's say that you connect these to the center. So let's define this variable as some theta, and this angle is some phi, right? So now if you notice really closely, the triangle that you have is gonna look something like this. You have capital R, radius on both sides, and you have a theta enclosed between them. So by like triangle properties, you can say that this angle, if it's phi, should be equal to this angle. So exactly, it's gonna be equal. So this is also gonna be phi. And similarly, if this is phi, so is this phi, so is this phi. So now let's just write a tiny piece of information here. We'll get back to it later, right? So we know that the angles in a triangle sum up to 180 degrees, which is basically pi radians. So I can say that theta plus 2 phi equals pi. And we'll just keep this like this itself, and we'll see how we might have to use it. So another thing is, we'll be using more geometry. So if you have any confusions in the geometry, it's good for you to go get it revised. So again, how do you write dA for this? We know that this is basically an arc of another circle. Like the circle is basically gonna look like something like this, and it subtends an angle of 2 phi at the center of this imaginary circle. So since this is an arc, the length of an arc can be given as, the angle between them is 2 phi, so 2 phi times radius. And again, let's define this to be small radius, and this of course to be the larger radius. 2 phi times the small radius. And again, this is just the length. We need to give it some thickness too. So let's say that it has a thickness of dr. So your dA is basically this. And integration of all of these dAs gives you the full area. So area is equal to integration 2r phi times dr. And we have phi over here, and we have phi over here. So we can further write phi as pi minus theta divided by 2. Now we substitute that, because we cannot integrate the angle phi over dr. There should be some sort of relation, right? So this basically becomes 2r times pi minus theta by 2 dr. The 2 cancels, and now you have r pi dr minus integration r theta dr. And again, since you have r over here and dr over here, this is integrable, or if that makes sense, I don't know if that's a word. So integration rdr, where r goes from 0 to 2r. I hope this makes sense. Here r basically scans across this entire diameter. So this is gonna become 2r the whole square divided by 2 minus integration r theta dr. And this just gives you 2 pi r square minus integration theta into r dr. And now we have to work out some relation that connects the angle at the center, which is theta, and the small r over here. So that's exactly what we'll be discussing right now. So if I draw the triangles a bit larger, this is what we're gonna have. So this is your circle, and I don't know why I even connected these. I don't think it's necessary. So since this is our point of observation, we should be connecting it like this. And this is your angle theta. And this is your capital R, small r. And I hope you understand why this is small r, because again, this is your imaginary circle, right? And this is like your center of it. I know it doesn't look like a circle, but trust me, it is actually a circle. Right, so this is gonna be center to the circumference, which just measures r. So now you have like this triangle, right? If you know a bunch of trigonometry, you can see that you can use the cosine rule over here. So cosine rule, which basically says that the cosine of this angle theta, or the general formula for it is, I'll write that one down too. If this is some a, b and c, and let's say that this is your angle b, or b over here, so cosine of b is equal to negative of the opposite side plus the squares of the other sides divided by 2 times the product of the other two sides, which is AC. So same thing over here, using cosine rule you can figure out that cosine of theta is equal to minus r square plus 2r square divided by 2 times product of r and r, which just gives you r square. Upon simplification, I can break this numerator down to give me half of r square by r square. And now a bunch of manipulations later, so you get something pretty simple. So I send this one that side and bring that one this side. So I get half r square by r square is equal to 1 minus cosine of theta. But now, if you have a very observant eye, you can quickly realize that I have a bunch of square terms over here and I have 1 minus cosine of theta. It'd be very simple if I were to just get rid of the square terms. So how convenient would it be if I could just take a square root on both sides? So in order to do so, let's create a square term over here. We also know that cosine of 2x is equal to cos square x minus sine square x. So we can write sine square x is minus of 1 minus cos square x, and you end up getting 2 cos square x minus 1. So how do I apply this over here? Well, it's the same thing. So now what I can do is, well, actually, uh, yeah, so converting it into cos seems like a bad idea. So instead, I'll be converting it into sine, because what we have over here doesn't resemble what we actually need. Because as what I was thinking is, you can send the 1 over here, so you get 1 plus cos 2x is equal to 2 cos square x. Well, this is not what I want. I have a 1 minus cos something. So instead, from this step, I'll be writing it as cos 2x is equal to 1 minus sine square x, 2 sine square x. And so I can write 1 minus cos 2x equals 2 sine square x. Aha, this is what I want. 1 minus cos something gives 2 sine square of half of that. So I can write this as 2 sine square theta by 2. Now I can send the 2 that side, and I have r is equal to, you take 2 there, you have 4 and 4r square, and you take square root on both sides, you have 2r sine theta by 2. This is an important relation that we have created. And another thing is, we also have, now if we differentiate this, because I see a dr over here, how about we convert the dr into d theta, right? So dr upon d theta gives you 2r times differentiation of sine theta by 2 gives you cos theta by 2 times a half, which just gives you r cos theta by 2. And since I am looking to write dr, I'm going to send the d theta that side, and this is what I'm going to have. Beautiful. So now let us just work out this separately, right? Dealing with integration theta r dr. So let's just deal with this for now, and then once we deal with this, we can just substitute it back into this. Let's just call this equation 1, so you know what I'm referring to in the future. So right now we have this as integration theta, replace r by this, you have 2r sine theta by 2 into dr, which is r cos theta by 2 d theta. And I see a 2 sine theta by 2 cos theta by 2. If I combine them, I get sine theta, that's all. So I get theta r square times sine theta d theta. I hope you know how this simplifies to this, because sine 2 theta is equal to 2 sine theta cos theta. This is multiplication, by the way. Yeah. So this is what we have. And now you basically have something like r square integration theta sine theta d theta. Well, there's not a simple integration. You must use integration by parts. But there's a simple method called the DI method. So using that, I think some black pen, red pen, or like there's a YouTube channel like that, he explains it very well. So you have a differentiation column and an integration column. For differentiation, I choose theta, and for integration, I choose sine theta. So this is called integration by parts. And I just put a bunch of plus minuses over here. And what's the differentiation of theta with respect to theta itself? It just gives you 1. And what's the differentiation of constant? Gives you 0. And what's the integration of sine theta? Gives you minus cosine theta. The integration of minus cosine theta gives you minus sine theta. And you just add the diagonals and voila, you get the answer. So this just becomes r square times you get minus theta cosine theta and minus of minus sine theta, which just gives you plus sine theta. And the integrating limits are going to be theta goes from 0 to pi. Because look at the diagram over here. You want it to sweep the entire arc. Even this diagram, you want this theta to basically go from that to that, right? So your theta is going to be from 0 to pi. So exactly what so substituting it, you get r square times, you get minus pi times minus 1, and this just gives you 0. Like subtract that from this becomes 0 and this becomes 0, so you get pi r square. But this is not the answer. Remember, this is just we've just dealt with this one thing. We have to subtract this, we have to substitute that into this equation. So that's what I'll be doing out here, substituting into equation 1. You get area is equal to 2 pi r square minus whatever we got, 2 pi r square minus pi r square, which just gives you pi r square. Doesn't it seem crazy that you get the same answer even after such rigorous integration? That just goes to show that integration can be used in many ways to find out like areas of all sorts of things. And I'll give you a little challenge. If you studied a little bit of electrostatics, then you must have an idea that your potential, electric potential, which is denoted by V, or even like voltage I guess, is equal to kq by r, right? So use this method of integration to find the potential at the edge of a disk of uniform charge density sigma. Yeah, and that's about it. So you have like a disk, it has charge density of sigma, areal charge density, and you are observing it from the periphery of the disk. So what would be the electric potential? So if you happen to solve it, comment it down. So see you guys later.